Good evening, bonsoir. And this is a last episode of this year of NeuroTechX Showcase Applications, Hardware and Software. Tonight we have April. Hi, April. How are you tonight?
Hello. Good, thanks. You?
Good.
Thanks for having
I'm
me.
really good. It's a pleasure. It's a pleasure. No, tonight is an exciting episode because we have a good topic. I think it's a really relevant topic, especially talking about diagnostics and neurodegenerative disease, and it's
hmm
about advanced tools for translational diagnostic image analysis. So it's going to be a great presentation, and we hope that the guests tonight will ask good questions. And then if somebody wants to come on video, just raise your hand. I can invite you on video. So April, do you mind me to present NeuroTechX for the audience?
Please.
Thank you. I'll be back to you in a second. So let me share my screen. Here you go. So I wanted to show you the neurotechx.com website and why this is relevant. Can you see my screen?
Yeah.
That's great. So this is for the audience. You can see what we do at NeuroTechX on this site. This is the landing page of the organization. And what is interesting is the numbers. So we do have communities all over the world divided into chapters. The chapters around the world in the different main cities are divided between students chapters and technical chapters. And you will see the distinctions in the Slack for NeuroTechX, and I will mention that in a second. But if you scroll down in the landing page, you see what is important, what is the culture, mission, and vision of NeuroTechX, which is community, education, and networking. So we have a focus especially on professional development. There is also a section for job search, and then we have testimonials explaining that. And next year, we will have a Buzzing Review 2022, which is going to be happening as coordination across different chapters all over the world. So without further ado, one brief mention to the Slack. So if you scroll down, you have a click button here. And then by clicking on this, you will be addressed to a form, online form. It's free. And then with that form, by giving your email and then stating your interest in neuroscience, neurotechnology, you will be automatically connected with the Slack. And then you will see there is a ton of channels, a ton of content, a ton of discussions, and you can connect for free with all the members. It's good for networking. Please use it. So I'm stopping sharing now. And one brief mention to the fact that the NeuroTechX site also contains a section where you can purchase wearables for a lower cost than the market price. So please also check that section. So I'd like to introduce our guest. So Khademi, Dr. Epre Khademi, is the leader of the Image Analysis in Medicine Lab, or IAM Lab, at Ryerson University, or X University, as it is a controversy now if it should be renamed. And we going back to the what April does is the coordination between work of engineers and clinicians, and it has to do with image analysis and machine learning. So April is also investigator for the Canadian Consortium of Neurodegeneration and Aging, CCNA, and also affiliate scientist at St. Michael's Hospital here in Toronto, and a member of the Institute for Biomedical Engineering, Science and Technology, IBEST. April, you work in development healthcare institutions in Toronto, and you collaborated also with important corporate healthcare companies, right?
hmm
You like to mention a couple of things for our audience about your industrial collaboration?
yeah. So actually, after I finished my PhD, I worked in the industry for 3 years before I became a professor. And so I worked at GE Healthcare and Pathcore Inc. And these two companies, I focused on the actual development of AI tools for medical imaging and the commercialization of them, as well as clinical trials. And that was back in the day when it was still called big data analytics.
Yeah.
So, but that was for digital pathology. It was a new medical image type. And so a lot of my research focus comes from those commercial experiences. They kind of guide the way that I design and develop tools.
So there has been a continuum from your your studies into professorship and industrial experience in between, right?
Mm-hmm. That's right. Yeah.
It's beautiful. It is also very relevant that you work in collaboration with St. Michael's Hospital. It's basically in front of my apartment building, so I can almost wave at people at St. Michael's. And I know that there is beautiful work and research going on there. So we're very happy to have you tonight.
Thanks.
And I know that you wanted to show us some content.
Sure. So thanks for the introduction, Chris. I'm excited to be here. I've taken part in a few other brain hack and neurotech panels in the past, and I think it's a great group. It's really neat to get a whole bunch of enthusiasts together that are interested in neural technology, and it's from all different types of technology, which is nice. So today I'm going to bring the medical imaging aspect to neuroimaging. And let me just share my screen here. And so I'm going to talk about some of the considerations for translating AI tools for medical imaging or neuroimaging applications. This could be a long talk, so I've just kind of given a few ideas that maybe that will spark some discussion. And
Sure.
So,
I
so
think,
the value,
yeah.
Can you see?
We see the window in front of it. Yeah.
Which?
Let's go.
Okay, sorry.
Let's go.
So, neuroimaging is particularly ripe for the application of AI, and that's largely because neurodegeneration and neurodegenerative disease has a high economic and health burden on healthcare systems. And so we need biomarkers for monitoring and stratification of patients. And to do this manually takes a long time. It's laborious and it's subjective. So now we can start to leverage AI tools for the objective, efficient analysis of disease and neurodegeneration. And that can also lead to new insights. So despite the value of AI to neuroimaging, there's no routinely and widely used AI tool for neuroimaging yet. And when I say routinely used, I'm talking by neurologists and neuroradiologists and radiologists. And why? We're just not there yet. There's a lot of excitement about translating these tools, and I believe that these will become commonplace in radiology across the board, but there's still a little ways to go. So I wanted to talk a little bit today about what are some of the things that the considerations that we can have as researchers that are focused on creating these tools in order to optimize translation opportunities. So some of them, and I will get into each of them, but basically the tool that you focus on should have a clinical focus. It should be robust, so it should work in a variety of settings and imaging departments. It should be explainable to a certain level, or that's still something to be debated. And then there's some integration considerations, which I use as an umbrella kind of to describe a few different concepts. There's a lot of different things that could be really discussed, like ethical AI, trustworthy AI. There's different aspects that are also of interest. So I've basically tried to take just a few of these and discuss them a little bit today. So the first thing, and a lot of times researchers have this problem of developing a tool that maybe is not actually going to be ever really translated and clinically used. So one of the most important things is to define the use case for the tool that you are trying to develop. And so for neuroimaging, there's really, I feel like there's four big buckets. And the first one is quantification. The second one is monitoring. The third one is stratification. And the fourth one is prognostication. And so really what you have to think about is how is the end user going to use this tool and what is their pain point that you're trying to alleviate? And so for quantification, the pain point would be, for example, manual measurement, whereas the AI tool can relieve these pain points and improve quality by increasing diagnostic accuracy as well as improving turnaround times for reviewing cases. There's longitudinal pain points, so actually measuring and comparing rate of changes. So you have neuroimages that you have to look at over time, and it's very tedious to try and manually measure whether there has been an increase in a volume of a small structure, for example. Mm-hmm. Then there's stratification, and this is where kind of AI starts to get really kind of neat and doing things that are maybe not currently possible with manual methods, is that we can look for sub-visual clues in the data that allows us to learn more about disease, and we can use these to, for example, stratify patients. We can for clinical trials, so we can put them put patients into homogeneous disease groups based on the biomarkers of their brain, and that can lead to more optimized trials. Another one is intervention point. So when do we actually intervene on a patient? The last one is like the future of AI, and this is really also quite an exciting area, is the prognostication. And that's to predict the outcome based on the current data that you have from the patient. Can you predict whether this patient would, for example, progress to advanced Alzheimer's disease? Yes. So just to give you an example, and anybody feel free to ask questions along the way. One of the example use cases, which is really, really relevant in neuroimaging and is for longitudinal monitoring. So this allows you to, in the ideal world, if we could image subjects' brains on a semi-regular basis, we are able to then see how their brain changes over time with respect to volumes, with respect to white matter or gray matter changes, ventricular enlargement. And we can compare these measurements objectively to normative curves. So this is kind of analogous to a growth model of children, or the growth model for children. We can actually say, hey, this person is progressing at a faster rate than normal. We think something is going on here. The challenge of developing these tools is longitudinal analysis is not easy. And that's because the change is really small and measurement error can be a concern.
And I guess, if you compare with a neurotypical, also you do have a question of what's the sample size to be, significantly different between the two cohorts, right?
Yes, exactly. And that's why more data is always better, right? But in order to process a lot of data, you have to do so robustly. And you have to ensure that it can translate to different scanners, different patients.
Yeah, there's a technical, device problem, but also there is quantification of the, Conway's D or the distance between normal populations that you evaluate. I know there are tools like GPower that do this calculation for you, and especially for atrophy, white matter, typical gray matter volume, and so on. Do you maybe we'll touch upon that later in your presentation? But do you do you have recommendation for best practices in terms of population size?
No, we don't, and that's because we are a lab that processes large amounts of data. So we're currently working with I believe we're at around 400,000 images,
Oh,
which are like from 80 centers worldwide.
probably
And
don't even have
so,
that problem.
no, exactly. I mean, we're starting to do some sub-analysis that we have clinical variables for, and then it's getting a bit smaller. But I mean, it's still roughly around 400 patients. So it's still a
Interesting.
decent size, which compared to literature, it's actually a lot more than what we typically see,
Thank you.
especially for automated methods. So that
Interesting.
actually brings us to the next great point, is that if you want to do that, if you want to process these massive data sets, you need to ensure that your tool is robust. And this is one of the key barriers, I believe, currently to true clinical translation and implementation. And that stems from a lot of different things. One of them, most notably in neuroimaging, is the type of scanning device that you use to acquire the images. GE, Philips, Siemens, they all have proprietary reconstruction algorithms, proprietary post-processing such as filtering. The way the case-based representation they use is all different, and this is all proprietary. So when you get the image as the engineer on the other side, what you get is an image, and you don't actually know the specifics on how it's reconstructed.
Yeah, but
So that's a bit tricky. Mm-hmm.
I know that in some, I totally completely agree with you, maybe for the clinician side on the user interface, but I know for sure that some researchers, for example, at the Donalds Institute, like Christian Beckman, for example, they use the API for Siemens in Essen, for example. So some of the key space parameters are available through functions of API. Is that also your
Yeah.
experience?
So like, well, yeah, like if you get access to additional information, that would be helpful, but it's not as easy as that, I believe, because even if I understand the way that the case space is used to reconstruct the images, that doesn't necessarily tell me the way that the noise is manifested in the image. It might give me some clues. It might, with multicolor technology, it's pretty hard to model the noise. It can be spatially correlated. It can be non-stationary.
That's true.
In some of the reconstructions, the sum of squares, I believe, reconstruction, you can actually kind of predict the type of distribution, but for all the other types, I don't know if there's a closed form mathematical solution for like the noise. So there's a lot of things that are happening in the images that are very vendor specific. And even if, let's say, they change, and sometimes even you can have GE and at one place and GE at another place, but for a particular sequence like T1 or T2, they might use very slightly different parameters. So their repetition time, their echo time, their etc. might be just slightly different, but it's still under the umbrella of T1.
Yeah,
So
and
these also create variabilities.
that's very interesting point actually, and I don't know if you want to delve deep on that, but just to mention that sequence programming is a bit of an art, right? Because it impacts on the quality of the image, and depending on the outcome that you want to see, planar images or volumetric images or subvolumetric images, or reconstruction of other kind of properties of the tissues, you would have to choose a different sequence, right? And then sequences also get patented, right? Because it's so complex that to have a certain outcome, diagnostic outcome, you also come to the point of patenting the sequences.
Yeah. So and the funny thing is that because I've been working in the space for some time now, so this was before there was a big push towards quantification and AI and all that. And so when I worked at GE, even though I was working at digital pathology side, I often talked to the MR physicists, and I tried to learn more about the underlying technology. And what I felt was that, the main consideration was image quality. So how is the image actually going to be perceived and looked at by the physician? And image quality in terms of SNR and CNR, so signal to noise ratio, contrast to noise ratio, as well as whether it's actually measuring the pathology of interest. Now, come to, a few years back, I believe all the vendors are now starting to think about what is the impact of the way they build the images on the quantification. So, it's great. It's great for people like me because I'm always left with the images and I have to try and clean them up. So if the vendor in the first place is actually starting to think about these things, then, maybe we can get some kind of a standard, right? Like some kind of a standard that allows us to easily deploy algorithms across scanning devices. And the reason why this is a problem is because you can see these images on the right here, is that these are roughly the same age subjects. And we've normalized the dynamic range. So the intensity scales are all the same on all the images. And you can see that the way that the skull looks is different from image to image. You can see that the actual brain tissue itself is darker from image to image. And this variability creates variability in your data set. So, brain isn't getting mapped to the same intensity range and values across scanners. So your tissues are kind of not on a standard scale, which is like CT has the Huntsfield unit, which is a standardized metric. So they know bone is between a certain Huntsfield units, whereas MRI has a non-standard scale. So even if you imaged yourself 2 times, you most likely would get different intensity ranges.
And interestingly,
so this causes problem.
Sorry, you want to finish your thought?
No, I was just going to say this causes problems because algorithms are mathematical tools. So they look for some kind of a consistency, some kind of a feature in the image that it can correlate basically across the data set in order to exploit it. So this variability generally causes trouble downstream processing.
It's true, and then on this account we also have, because you said that you are plotting a standardized dynamic range. We have a question from the audience, and please correct me if I'm wrong, if I say something wrong, Epre.
Sure.
One question from Kirsten. Hi, Kirsten. She asks, interesting to think about scanner differences. And what can you say about differences in the field of view? For example, when the cerebellum is cut off of the image for some patients or recordings, how can one deal with that? Because that will impact, in fact, the dynamic range, I guess.
Yeah, so definitely the field of view matters. Also, things like slice thicknesses really matters as well for these kind of things. So if you there is that level of variability as well, spatial variability. So what I've kind of been talking about is kind of like a noise distribution variability, intensity variability, but also there's a spatial variability because maybe the cerebellum is cut off. Most protocols should generally, neuroimaging protocols should include the cerebellum, but sometimes the patient's head is moving in the scanner, or sometimes patients have small heads. And so these are all create another dimension of variability in your data that if you want your tools to be robust, it kind of has to consider this in the design.
Thank you.
Okay. So because there's all these types of variabilities, there's even disease variabilities, right? And differences between men and women, for example. So how do we actually prove that our tool is robust? So one of the things that we've been developing in the lab in the last few years is validation frameworks. So, and it's a way to kind of put these tools to the ringer and see where their strengths are and where their weaknesses are. And we don't just focus on accuracy, which has been the de facto standard for many years, because what we also need to know is it going to be reliable? Is it going to work on prospective data? So that would be the generalization. So we looked at across data sets, and we also looked at across scanning devices. We also looked at whether there's a robustness to pathology. So let's say I'm trying to measure ventricular volume, and some patients have normal ventricles, and the lateral ventricles are small, and sometimes they're almost like barely visible in certain slices, whereas somebody with advanced dementia or Alzheimer's would have large ventricles. So you want your tool to work equally well as for less diseased patients as for the diseased patients. And so we created this kind of framework where we even tried different testing and training strategies. And we looked across like 3 different areas, and we even took it to another a dimension in another work. So basically you measure performance across these dimensions, and this allows you to establish proof of effectiveness for your segmentation or your biomarker tool. And you need that for clinical trials, for wide scale adoption. So I can show you some of the results. These graphs are a little bit busy, so I'll just kind of try and highlight some trends. So this is the performance metric, okay? We use something called the dissimilarity coefficient, which looks at the predicted segmentation versus the ground truth segmentation, which is a manual outline from the radiologist. And we, in a very lay term, we look at the number of pixels overlapping as our metric. So what is the agreement between our segmentation, the automated and the manual? And so what we started doing is we started to try and divide. We've looked at several different methods, okay? And we tried to look at the performance as a function of scanner. And we statistically tested for different methods whether the performance is the same across these scanners. And for many of the latest and greatest tools, the performance actually is found to be statistically different or significantly different between scanning devices. So while the accuracy might be higher, this variability across scanners can create measurement variability. And so when you're doing things like longitudinal monitoring, this little bit of measurement variability between Siemens and Philips can create and inflate your signals.
So Siemens is blue and Philips is it possible to enlarge? Thank you.
Mm-hmm.
Yeah.
Oops. So I actually use 2 data split strategies. So maybe this is interesting. This is a techie group.
Yes.
So in the first one, we took all our data sets and we mixed them all together. So we tried to keep it even between GE, Siemens, and Philips. But we used, we used 3 different data sets here, 2 for neurodegenerative disease, 1 for vascular disease. And we trained our models. And then, so these are 2 unsupervised methods, and these are 3 deep learning methods.
Mm-hmm.
And we tested then on the held out test set. So you can see the deep learning methods far outperform the traditional methods. So the traditional methods are unsupervised, or just like, I believe, random forest classification.
And the metric is segmentation
DSC.
of. Yeah,
and this case, I think it's lesions. So it's white matter and hyperintensities in the brain.
Mm-hmm.
And we're looking at the overlap of pixels that we found with the gold standard of the radiologist.
Mm-hmm.
And so in this scenario, you can see that, the performance, although there were statistically significant differences between the scanners, that it's overall higher, right, for the deep learning method. But so we decided to investigate something called data split 2. And this is where we try to really simulate what would it be like to develop a tool and then go and try and apply it at somewhere else. So let's say I developed the tool in my lab. I had a single data set, and it was comprised of GE, Philips, and Siemens 1/3, 1/3, 1/3. And we developed the same model. And now I'm going to go apply to, let's say, St. Mike's, for example. Okay, so I'm taking the Ryerson tool and I want to take it to St. Mike's. So these results are all for data that was not seen or not part of the training regime. So this is unseen data. So you can start to really see that the performance starts to get a little bit different. Performance is lower, even for the deep learning. So that means there's a drop, right, in performance. And also Philip seems to have some kind of a wonky trend there.
Can I ask a question?
Yeah.
So is the difference between data split 1 and data split 2 a difference in sampling cross-validation strategy, or
so
is
it's a training data? It's a difference in the training data. So this is like
okay.
a single center. I've used a single center. This I've used like 10 centers. So I'm using a mix of data. All the data that I have at my hands, I use a mix, and then it works well on the held out test set from all those centers. But when I use a single center, so one institution, for example, and then I try to test on the other data sets, you can see that there's a performance drop. And this is known as like a generalization problem, right? Because, and for true translation, that matters, because for a long time, the way industry was doing it was they were trying to tie AI solutions to their hardware. So they would say, oh, I'm going to develop, a Siemens AI tool. But that means you would have to have a Siemens scanner. And I think vendors are starting to realize that that's not practical. So they're starting to go towards more of this solution. So integrating the data from multiple vendors, multiple sites to ensure that you get this better performance.
Interesting. What do you think is the difference in performance due to when you use data from different sites and keeping consistency across devices?
Well, I think that deep learning learns a highly nonlinear, complex relationship in the data, and so it learns something that is data set specific or scanner specific. It might be related to the noise distribution. It might be related to some other statistical, high dimensional property. It could even be the cohort, for example. So like, let's say everybody's vascular disease in this one. So there's something that it learns that is particular to the data set. We're noticing that there is a big one towards scanner. And that's like a problem when you want to have a vendor agnostic solution, obviously. But so when you use a mix of all the data, it is seeing some of those noise distribution, some of those textures, some of those things that make a data set unique. And it is able to then, it's learned the patterns, it's able to then more effectively predict. But in this case, for example, because it's only seeing the patterns from one set, it is not able to effectively generalize to the unseen data, because it didn't learn those patterns. It hasn't been exposed to that data.
Fascinating. So it's almost like, deep learning looks at the different senses as almost as if every center has its own lens, on the different brains, and then because of calibration, it seems like calibration or background noise or magnetization vector, who knows?
Yeah, and so like this is the $1 million question, right? And this is kind of like really where the state of the art of my field is right now is, and even computer vision, because medical image analysis stems from computer vision. We have inherently our own challenges, like these domain kind of generalization problems. But we're trying to figure out ways now that we can minimize the impact of this data. Another thing that also might contribute to this good performance is that by showing this, the classifier like more variable data, it learns more broad representations. So if you show it the same thing, when you give it on test one that looks a little different than everything that was in the pool, then it's not going to be as effective. But when you expose it to a highly variable data, then you are able to learn or be able to predict better because you have a more wider representation, if that makes sense.
It makes a lot of sense to me. And then the question would be, the held out samples are also having the same proportion across different centers, I expect, right?
Exactly. So we try to keep it matched as best as we can, but we have centers and scanners and then we have data sets. So there's a lot of things to stratify by, but we definitely try to keep the proportions equal.
Interesting.
So yeah, we don't need to get into this as much, but I'll just quickly highlight here. So this is actually by, oops, sorry. My mouse has been doing this to me all day. Okay, can you see it again?
I can see it.
Okay, so this is by data set, okay? And you can see, so data set is just like, for example, like one clinical trial versus another clinical trial. So these are all multi-center studies.
Could
but
you
you can
make it
see
slightly bigger?
Mm-hmm. How did I do that before?
Is it Windows?
Mm-hmm.
The mouse pad is probably, a pinch
There
out.
we go.
Yes.
Yeah. So here you can see that each one of these colors are different data sets. Okay. And they have all GE, Siemens, Philips. They have all multiple centers, like the ADNI data set we have, I think is 60 centers or 70.
Mm-hmm.
We have Kane, it's a Canadian data set, which is 10 centers, CCNA 12. So you can see that once we go to apply the data, apply the tool on new data, it gives you variable performance. When you use the mixed bag, right, it's a lot better. You can see it's more accurate and less variable, but there's still noticeable variabilities. And this means that when I go to take my tool to St. Mike's, that it might not work exactly as I predict it to, pretty much. And that's a problem for translation.
Yeah, it's interesting. This is comparable, the left panel figure is comparable with the previous left panel figure.
Exactly. We did it by scanner over there, and this one we did it by data set.
It's the difference is probably that those data sets, pre-collected data sets, have a different number of centers across data sets. Say Kane is probably 60, and then the ADNI is, I don't know, 120. So that's probably the only difference. Whereas, beforehand, you had different, probably you could stratify better your patients with the same proportion for the previous graph. Correct me if I'm wrong.
So we still try to stratify the training data. It's the same models. We're just measuring on the test performance here. So there could be differences in the sample sizes per group. I think there was for sure. But the main point is that the testing performance is different depending on which data set that you're working with.
It's expected probably. So if the blue one has a bigger sample size, probably it's performing better.
This one actually had the smallest. This one had 12 subjects. So we're looking at a whole bunch of ways to overcome this. How do we actually make it more consistent? And there's things like domain adaptation. There's a standardization that you can apply. And so we're actually hopefully going to be publishing a paper on that soon. looking at different methods that you can actually do to overcome some of this. So there's another topic that's kind of an interesting one in the community these days, and it's the one of explainability. And the reason why this is a kind of an interesting discussion topic is because, one, a lot of the clinicians that I work with, while they are ready to embrace technology and they're excited about the way AI will augment their practice, they're also like to understand what is the decision, how is the decision made? Because at the end of the day, in terms of legal liability, most likely the radiologist is the one who has to sign the case out. So they use the diagnostic tool to make their decision. And so some of them feel, and this was more so a few years ago when it first came out, that some felt that they would like to understand more about how the tool is making the decision. And this is also important because if you want to learn about mechanisms of disease, because if you don't understand how a tool has made a decision, maybe you don't understand what is different between patients. That's important. And that's good for treatment and stuff like that. The challenge with that today is that in order to get high accuracy, you get a reduction of explainability, right? Yeah. So those highly explainable, even thresholding methods that you used to use with handcrafted features, while they're highly explainable, they're actually have low performance. So there has to be some trade-off between this kind of accuracy and explainability.
I understand this, and I think for the audience to put it in simple terms, I would say, and then you will correct me if I am saying something wrong, Epre, but to me, what my understanding of explainability is the difference between a blood pressure reading, which is a number between 80 and 40, and the weight of a neural network, which what is that, right? So a set of weights of a neural network with numbers. It's unintelligible to the human being, but it's very useful for the machine learning decision maker. On the other hand, the blood pressure scalar number, it's very interpretable by the clinician, but it will have a low accuracy if inputted in the machine learning algorithm. So that's the machine-human differential there. That is this explainability, right?
Well, like I can give you another example. So let's say I'm segmenting the brain. I'm segmenting a lesion, right? I can get things like volume, texture, size. These are all features that is easy for the clinician to relate to. They say, okay, that's a big lesion, that's a small lesion, that's a bright lesion, and so forth. With deep learning, like especially with classification tools, it just provides an answer. It provides an answer and a confidence rating, which is great, but it provides will advance to dementia or Alzheimer's disease. That's the decision. Right? So understanding how it actually came to that decision is where this whole kind of black box phenomena has come. And that's...
It's well said. Yeah, it's a black box approach because you cannot go in the guts of the machine learning algorithm and say, oh, I understand these numbers, like the blood pressure. You say, okay, I trust you, black box.
Right, exactly. And so this has been debated in the last few years, the black box, especially for in medicine, like, should we use it? The thing is that these tools work and they're effective and they get good accuracy. So, we have to try and find a good balance between accuracy and explainability. And so this article was written a few years back. And basically it says that when a black box is valuable is that is when they produce the best results and when the cost of a wrong answer is low, or when they inspire new ideas. So that was kind of the going idea for it for a little while. But the Blackbox offers the best solution that's currently available. Like you saw, the accuracy was much higher than the traditional approaches. So I'm getting more accurate results. So in order to kind of start to learn what's inside these so-called black boxes, researchers have been starting to build interpretability maps. And what these do is they basically combine information from the different layers of the neural network in order to understand what areas in the image were important for making a decision. Okay, so you can see in some of these images here, this is the layer-wise relevance propagation heat map. And this gives us the areas that were seen as important or were heavily influenced the decision in the image to make a classification. And I believe this was all AD classification. So they were doing between, healthy controls and Alzheimer's disease. So you can see that the areas that were important for making decisions were some of the cortical regions, which we know atrophy is occurring, and some of the other regions in the brain. So there's a lot of discussion about ways that you can try to open up the so-called black box.
And the left hippocampus or right hippocampus.
I think the hippocampus was in there as well.
It's a big star-shaped hit.
This one here.
Two hippocampi, yeah.
Mm-hmm.
Well, left is right here, right?
Exactly, yeah. So the last thing I kind of wanted to discuss was for real translation is, and I mean, integration is kind of a very loose term here, but it's actually like putting these to real use in the clinic. So in radiology workflows. So how do you actually do that? Okay, you've developed some really great tool, you validated it, you've rigorously shown that it works equally across all scanners, etc. And now you want to try and use it on prospective data or use it in an actual clinical workflow. So first thing you would have to do would be to actually technically integrate these tools. So a lot of them, like DICOM is the main medical imaging standard. So you'd have to basically work with DICOM APIs in order to integrate your tools. I think some of the vendors are getting a little bit better at allowing this and making capabilities available for this. The other challenge is also, depending on the API, is, talking to all the different aspects in a medical imaging department. So we have PACS, we have RIS. These are all the data management servers that house the thousands and thousands of images and clinical data. So in order to run your algorithm, you'd have to access this, and there's integration hurdles. There's sometimes, most of the time now, we have vendor neutral kind of solutions. Mm-hmm. But there's still some proprietary ways to do things. So it's not seamless. Like if you say I build a DICOM solution, it's not going to necessarily just plug into everybody. You have to,
of course.
Mm-hmm.
It's understandable, right? So, but a DICOM is such a format that allows for collection of images data, but also metadata mm-hmm. about the subjects, mm-hmm. right?
Exactly.
We know the importance of demographics, for example, come up with the Alzheimer's disease prognosis and diagnosis. Mm-hmm. We know that early stage disease detection is more important, so age as a metadata is important, and then you want to have a stratification of, distribution of education mm-hmm. for Alzheimer's and so on. So these are all important, and they are stored in, I believe, everything is stored in a DICOM format, right?
That's right. And there's also other things too, right? Like, so for example, does it make sense to process the images on the fly, right? So, okay, the radiologist has been assigned this case, and does he or she turn on the algorithm and look at it? If that's not the case, you most likely, depending especially on the how computationally expensive the algorithm was, would you want to run it offline? So when the case comes in the queue, you automatically know it's the neuroimaging protocol. You run it, you save the results, and then when the radiologist goes to review the case, the overlays come up, like as I show here, for example. So it would be instantaneous instead of having to wait, for example. So in that case, you would have to, there's also other considerations into how to implement it.
Almost interesting that, so you use the layoff time between recording and diagnosis to be able to, so if you if you process it, so if you put in place a streamlined process to have that pipeline or funnel in the clinical practice adopted, that is going to be beneficial for the clinician to have the results plotted as overlays.
Exactly. And especially, even though you can do a lot of this stuff in the cloud, like you could run the algorithms in the cloud, for example, there's patient privacy concerns. So in Canada, it's pretty tight, actually. I think it's not really allowed to take patient data and put it in the cloud. So if you want to run a deep learning algorithm, you need a GPU for that. So most radiologist workstations won't have that. So it would probably make more sense to do it at a centralized location, like in the hospital, where the servers and everything, and then save the results for when he or she reviews it.
Isn't there now a protocol called HL7 that is sort of safeguarding this at the clinical level? So
I know a little bit about HL7. Yeah.
Yeah, that could be some cloud solution as well, right? Just taking it to the extreme.
Yeah. Well, this is the ideal way of doing it. But because of patient privacy and worry about, data breaches and hacking and all that, I don't think in Canada, we have not embraced that.
So adoption is going to be slow.
Yeah.
Understood.
Actually, that brings actually to the next point, which is impact. So in order to adopt some of these tools, right? Is it going to be really annoying to try and integrate the tools, and it's going to have to be a customized kind of thing? So that's one thing, obviously, is that, it has to be practically doable. And I do think it is. I think we're there. It's a little bit messy with the different vending solutions, but we're there and we can do it. And I believe some vendors are doing it, but whether it's used routinely and for widely, I don't think that's happening yet.
Yeah, but we have a question from the audience on this. Actually,
sure.
MJ, hi MJ. He or she asks if you do the or the processing instantaneously, like you said before, April, could you also have an in-between step, quote, image quality too bad, and then scan again immediately?
Yeah. So that would be very good, actually. I wouldn't do necessarily the processing first. It would be good to do the image quality detection first, because algorithms, while they, can do wonders, they're not magic. So if the image has a problem, if the source is problematic, then you won't get good results. And, sometimes the radiologist might not like to read that image either if there's heavy motion artifact or there was some kind of error in reconstruction. So
some metal plate.
There's a whole bunch of different things that can cause different artifacts. So if you could have a QC pipeline that basically evaluates the quality of the image and automatically deduces, hey, but that would be more on the technician side, right? So that would be something that would be flagged for the technician. And because then the technician would say to the patient, you need to stay, and we have to do it again. And then from that point, if it's clean, then you could say, okay, activate the algorithms if it's past the QC.
That's a great point.
If that answered the question.
I think it answered it for me. MJ, please comment on the text if you're satisfied, but it's a great answer. So technician, but also clinicians, and in a second run, they all take responsibility for adoption, but also to have a streamlined pipeline. And it's also about best practices in a clinical practice, I guess.
Mm-hmm. Yeah, exactly. Like, you know, and in addition to the, like, you know, making sure you have an impact, like your tool works and it's easy and it's, you know, you also have to think about how does it going to actually improve the quality of care, right? So, okay, we've spent hundreds of thousands of dollars to develop a tool, sell the tool or buy the tool. And now what is the impact actually that this has? And from a business perspective, the business side of things, they like to look at things like turnaround times. So my tool will make your radiologist faster. They will read more cases and you will be able to bill for more cases, essentially. But then from me as a researcher, I really actually like to, you know, I care about turnaround time. We do think about that. Especially some of those complex cases that you think like maybe take multiple days and stuff like that. I definitely like to try and speed it up. But if it's for like my personal interest is actually how do we make something better for the patient, you know? So like have an impact on society and humanity with your technology. And, you know, but for neurodegenerative diseases, measuring this impact, how do you actually measure that? It's a bit tricky because, you know, there's not a lot of drugs that are approved for like dementia and Alzheimer's. So, right. But
it's a 98% failure of current drug system on Alzheimer's. Correct. 95, around 95, 98% lack of effect.
Yes, I believe you and I were talking about this before we started that, you know, all current Alzheimer's drugs focus on amyloid beta clearance, right? And so amyloid beta is already accumulated in the brain and it's already started to cause damage. And by then it's a little bit late because the damage, you know, you can't regrow brain basically.
True.
And so once it's a lot of times irreversible brain damage. So one of the impacts would be to, you know, try to develop tools that can help to help with clinical trials that are maybe not focused on amyloid beta, but for example, being able to stratify patients into vascular disease patients with cognitive deficits and patients with Alzheimer's pathology. Maybe the patients that, you know, don't have Alzheimer's or amyloid beta accumulation would actually benefit from something else, like, you know, just even lifestyle changes. So exercise, you know, diabetes. So you could find those patients, stratify them, find them early enough, say you're on a bad trajectory and we need to intervene. And
that's part of assessment. In your input NLP graph here, there is a big assessment board at the center. I guess preventive medicine, whereby you can assess and pre-screen according to some, you know, approved GP, you know, control praxis in a way, it would be beneficial. And like you say, maybe big cohorts. I don't know if you have that in your 400,000 datasets, but if you have cohorts of at-risk patients like diabetes, like you were mentioning, that did not develop cognitive science yet for any reason, regardless if they accumulate amyloid beta or not, I wonder if this assessment could be done with imaging already. So if you see something that is related maybe to functional MRI or functional imaging with CT or the likes, who knows, PET aspect, that has to do with also metabolism, functional electrical activity, bold signals, and so on, that is not yet reflected in a cognitive impairment. Can you see that with MRI or other techniques?
Definitely, and that's actually something that we're working on. Like, we're actually trying to see whether we can find some of these earlier clues and look at the trajectory of the patient, right? And so for that, you need longitudinal data, and you also need low measurement variability, because as soon as you start to compare time points, the changes can be small. And so if your measurement variability is higher than the change, then all you see is noise. So you have to make sure that the change that you're measuring is more than your measurement variability. So that's kind of the trick, is that, but it gets a little bit more easier to see some of these trends when you're processing large amounts of data, because you just have a big sample, and then the signal comes up and the noise goes down.
What would you say? It's clear that having more data allows you to model better this nonlinear commonalities, I guess, to be predictive with your deep learning algorithms that you're promoting. I was wondering if, to your, if you have a gut feeling of what is the combination of, independently from algorithms, what is the combination of either techniques, or in the sense of MRI, fMRI, or sequences, or metabolism versus electrophysiology? What is the combination of the single most sensitive and specific technique that you have seen so far, or there is no such a thing?
Wow, that's a difficult question to answer. Because, like, obviously I'm a little bit biased because I work in imaging. So, and imaging, the nice thing about imaging is that sometimes, damage is occurring, but it doesn't show up in cognitive symptoms. So the patient can be fine and they don't actually have cognitive deficits, but neuroimaging captures that in real time. So in almost real time anyways, because you have to have some kind of a breakdown or some kind of a circuit not working in order for there to be a cognitive deficit. So it's more real time. But that being said, imaging is probably only one of the aspects, right? So that's actually showing the damage that is occurring or is there already. But there might be other things, such as, like, for example, EEG or blood pressure or vascular risk factors. So, like, do you have hypertension, or do you have diabetes?
Good point.
So clinical variables like that is also very interesting. The consideration that when you start to integrate all these different modalities is that you have to think about how are you going to use it in the real world. So, like, in one of our data sets, we have some very nice blood biomarkers. We have amyloid beta blood biomarkers. We have a few other ones, tau. If I develop a model to use that information, right, when I want to test it, you also need that information.
Of course.
Right? Yeah.
And you need to test it also on neurotypicals, and then have a CSF spine tap on a healthy person is not really advisable. And so how do you train your model, right? And that's why I was thinking, picking up on what you said. So if you're done and don't want to finish your thought, I don't know if you want to say something else.
No, please continue.
No, I wanted to pick up on what you said before, because one of the, now Alzheimer's disease diagnostics and then screening, pre-screening is going heavily, towards, blood biomarkers, because there are reagents that are probably very effective, and that's the promise. On the other side, I don't believe that we should focus only on one diagnostic technique, because we don't have to follow one specific business model, but we have to follow science, and in specific machine learning and how to build a model. So variability and robustness aside, that we mentioned, could be a problem if you don't have an homogeneous training data set. Those techniques that, for example, exploit portable, low cost, low risk, low invasiveness, and a slightly different technique such as EEG that you mentioned before could be interesting, such as, for example, I know of a company that is in a portfolio of a company I work for called Vistim Labs in Boston, that uses a biomarker that uses the visual evoked potentials differences between cohorts of neurotypicals versus non-neurotypical, to exactly detect what you were talking about, which is early stages of dementia, any sort of dementia, because we know already that the homeostasis of the visual cortex cells is already disrupted by the systemic disease, be it vascular or non-vascular, by the position of proteins or other peptides. So we do know that something happens at the level of the neuronal conduction of electricity even before that any cognitive impairment happens. So such as a technique, for example, could be advised. So my take out of what I understood is, for machine learning predictive models, so to improve your level of predictiveness, everything works, anything goes, in fact. So the more information from more convergent, independent evidence is well seen. It's almost like having a classifier, training a classifier with different labels, and we know the labels, right? So because one label is neurophysiology, one label is metabolism, one label is volume, like you see in these overlays, one label is anything. So if you can tap into the real phenomena that happens at the cellular level, you win.
For sure, because you're also, you like, disease is not this linear process where it's one modality is going to be enough to explain it. I believe that it's probably multidimensional, and therefore using these additional modalities to diagnose would probably increase it, because like, for example, the example I gave you was that, okay, we see certain things happening in the brain, and that's the damage that's occurring right now. But that doesn't tell us the whole picture, right? What caused it? What's happening on the cellular level? So, even things like proteomics, genomics, all that is, that was one of the big exciting things, I believe, when kind of big data analytics came to town, and AI. It was that, okay, we have these computers that now can process a lot, right? And we can also start to integrate these disparate but related data sources that, to get a better picture of what's happening.
Well, now it's exploding. The field is exploding. I'm fascinated by the latest discovery, for example, that not only do you have in genomics association of multiple classes of SNPs with a disease, or multiple diseases with a SNP, so it's both ways in a genes, but you also have a better understanding of transcriptomics, which is that 95% of the genetic code that doesn't encode for any protein, but seemingly encodes for the timing of encoding of proteins. So
that's the thing, right? Because you can have certain genes that maybe predispose you more to dementia or Alzheimer's, but you actually don't know whether you're going to get Alzheimer's, right? So your genetics can predispose you, but there's something else that's happening that makes those people actually progress to Alzheimer's. I think it's environmental, or
And people might ask now from you, how can it be that an environmental factor influences how genes encode proteins? It is possible because genes are also active, elements inside the body, and they can wrap themselves up or unwrap themselves up according to what happens in the nucleus. So it's a fascinating field. It's not well understood, but we just keep an open mind that genes encode proteins, but also the sequence and the timing of encoding of those proteins, the activation of these genes is also something like an open field.
Yes. Yeah.
We do have a question from Kirsten. Do you want me to read it?
Sure.
I think it's referred to the machine learning algorithms. So I'm reading the question out loud. So April, you mentioned the clinicians and radiologists over last years got more used to seeing the usefulness of machine learning algorithms, including deep learning. But what would be your strategy to make sure that the patients understand and are comfortable with decisions being made by a black box? For example, being classified as at risk, or even worse, risk of death for a patient, given something as a decision making done by a black box machine, right?
Yeah, so that's actually a really great question because, a lot of times the discussion is how this is going to help the clinician and the patient and how they feel about it maybe is not as much discussed. So practically, I think going forward, because of the way, it really depends on how this unfolds because right now, will the radiologist sign the report and say, I use this tool to help me make a decision? Or will they just sign the report and say, okay, dementia, for example?
I know better.
Yeah. So, and so what gets filtered to the patient is not necessarily how the decision was made, but what is the decision, right? Because we're currently, what the radiologist does to many of us is still kind of a black box, if you think about it, because we actually don't know the process that they do for diagnosis. But it doesn't mean that we couldn't do some kind of, community kind of perception, just because, let's say you're right, maybe patients, when they hear this, they think some computer is diagnosing me or something like that. But
I think
the main
on a fictitious note, probably every physician on their lab tech should have powered by AI if they take that consult from the algorithms.
But the thing is they're going to have tools from so many different vendors. So I guess if they're solely responsible for the decision, then a broad statement like that would be okay. But because those are legally binding documents, probably, like if the AI tool was making the decision, then it's actually the AI tool and the company that's liable. So, but right now, the way that all the companies are making it is that they offer a secondary read, or they give some measurement that makes the radiologists. I can give an example of that. So, like triaging, right? So let's say certain cases like mammograms, right? I think like 90% of them are normal. So so a lot of talk is about triage tools, right? Because we just highlight the top, okay, we know 10% is abnormal, so we highlight the top 20% and we give that to the radiologist. So the tool is literally making a decision on which cases the radiologist reviews or not. And in that case, I believe the company would be liable if they missed something, right?
Big topic.
So
I think,
it is a big topic.
also to waive liability for the companies. This is an assistive tool, so instead of artificial intelligence, it's more like intelligent assistant, IA versus AI debate, right? Where the intelligent assistant, which is the so-called expert system from the 80s, doesn't take the decision for the clinician, but is an assistant like Alexa, is assisting us
Yeah,
instead of using our hands, and then can give you
it's a
some
measurement
hints.
device.
Yeah,
It's a measurement tool that lets
but
you measure things.
the best diagnosis is done by the team of human experts at the end of the day. It's triaging is also a bit risky because there is going to be a case over 100 million that is diagnosed as a false negative
For
independently.
sure,
So
for sure. It's not perfect, you know. Another case of making the answer would be, you know, it reads the image and gives the result, and that's what's put in the report. So then the AI is the one that's making the decision, right? That the radiologist doesn't even look at it. But the way that it currently is unfolding is that these are going to be tools to augment them and their daily tasks, not
that's it.
do the decision for them.
Yeah, so we completely agree about that. I sympathize with what you say. AI is not a substitute for the human
No.
intelligence. Is not good to read AI as the artificial intelligence of the humans. Is more the assistant of the human at the moment that is taking the
Exactly.
decision. And humans are
Yes.
biased. We are also not perfect, but a team of experts that checks each other is almost perfect together with the intelligent assistant.
Yeah, and so maybe those are the things that would be good to communicate to the patient, is that we still are depending on human expertise. And also, some of the prospective studies would be really helpful in this case. So, using these tools, can we show that, diagnosis is more accurate when used in conjunction with the radiologist? Um, and so
That's
that
really
would be
cool.
something that's reassuring as well, right? That, my doctor is using a tool that helps to make them more accurate. And I think that would be helpful as well.
I think in this is there's a book in the other room that I'm reading that has been used, for example, for uh, flight pilots and surgeons, and it's called the Checklist Manifesto. I don't know if you read it.
hmm I
In
haven't read it, but I've heard of it. Yeah.
actually, in terms of decision making, it's a the point of this book is to advise to have very clean and tested checklists because they help you in during when something hits the fan, they help you out a lot. And then that happens a lot. It doesn't happen as often in during the flight, but that happens a lot in surgery, for example,
hmm
and depending on many factors. So I've been fascinated, and I made the connection association, free association here. Forgive me for that, but I made the association that maybe in this impact assessment and decision making topic,
hmm
having maybe a checklist assistant as well could be for the clinical practice, depending on what kind of decision you have to take.
hmm
It could be
hmm
some maybe connected also with the algorithmic part.
hmm Yeah, I definitely agree. And like sometimes what the tools can provide are relatively benign. And I say that because all disease and pathology is important. But for example, like a volume of a structure, right? If you're off a couple milliliters, it's not really that big of a deal. And most of the time, the algorithms can do things like volumes better. So, like, you could have a checklist that says, okay, what is the volume of this structure, this structure, this structure? And then you can use that to plot into your kind of normative curves and see where those patients are. And so the radiologist would still be the one making the decision that this patient is progressing too rapidly and or this patient, is showing early signs of dementia, for example, in terms of neurodegeneration. It's quite possible.
This is a fascinating topic. I see is this your last slide?
This is my last slide. So I had only one more point, if that's okay for me to make.
Absolutely.
So one of the things is, okay, so we built these things, we found the clinical pain point of the clinician, something that will add value to the organization or to quality of care, pain point. Then we've tested it, we've tried to make sure that it's going to work on all different scanners and centers. We've integrated it. We know what the clinical impact is going to be. And now, if you're a company, how do you actually sell these? So what is the actual pricing model for trying to sell these? And that's not a trivial question, because there's a lot of different ways that you can do it through licensing, like yearly licensing, per user, per case. And so, but what do you actually charge, right? So and in order to do that, a lot of the companies are trying to, for example, look into health economics, or like things that they could show has value to the organization. So like I was saying, turnaround times, if they can come to an organization and say, we can guarantee to make you 10 times faster, then an organization will say, okay, if you make me 10 times faster, I can charge 10 times more cases. I'm going to make $1 million more a year. Okay, I have enough money then in order to buy a new system, a new fancy AI tool.
It's customer value.
Exactly. So, like when I was working in the industry, pricing models were discussed quite a bit, because what do you actually charge? And so there's reimbursement codes in the US, and a lot of it was geared towards that and tiered towards that. But those change every year. So I initially remember they were trying to do like a per click option. So if I have my MRI here and I click it, okay, or one case, I get charged for that. And that was because there was reimbursement codes that and this was on actually digital pathology. So surprisingly, like in 2013, digital pathology was cleared for use in medical reimbursement. So all the companies were all over that, because they knew that the government would give like $150 a case if they used image analysis. And so what the companies were doing was saying, okay, you're getting 150 for that, we want 50%. And so they were trying to do it like that. But then the reimbursement changed from year to year, and it dropped one year, like to almost nothing. So then that failed. Yeah.
What was the problem? Was that medical billing CPT codes was reassigned?
I just think that it was getting less and less every year. So it started at 150, and I think it went down to like much less, like $50 or $30 or something like that. I don't remember the exact. Exactly.
The pricing was not made by the company, but was made by the system. So if you have a price model that is depending from an external entity out of the company, you don't have any incentive to have a full feature product to put out there.
Exactly. Yeah.
That's interesting. Would you like to zoom in the pricing strategy and then take us by the end on some of the points here? I find this topic interesting.
Okay, I can, yeah. So, some of these pricing strategies I'm not too familiar with, but like some of them I can tell you a little bit about. So this like freemium pricing, right? So this freemium is like give something for free, and then I might be mixing up the models. And then
charge other features added on top.
Exactly. So you give them the viewer and then say, hey, but we have all these apps. Do you want that? So this penetration pricing is probably like low, right? Like some way for you to get in the market and get some adoption. Um, this psychological pricing, this might actually kind of apply a little bit because um,
Perceived value of the app, or saving life or something,
exactly, yeah.
or
And
promotional
bundle
pricing.
pricing,
Oh yeah,
like yeah, like hey, you buy my scanner and I'll throw in some AI tools,
yeah.
right? And like you buy an
Transversal market.
MRI is like 3 million. So
It's yeah, for a 3 million scanner, sticking
you
sticking in
better throw in a few
throwing in
apps.
50K app, it's okay.
Yeah,
Promotional
exactly.
pricing is something like exploiting the brand of the company. Maybe GE comes out with this
Hmm.
fantastic scanner plus app. There's probably a marketing campaign behind that.
And then there's this dynamic pricing that probably fluctuates, maybe depending on the market demands.
Or what you said before, that the a regulatory entity or
Hmm.
some governmental insurance institution says that pricing should be going down because of regulatory reasons, and then the company is tied to that.
Yeah, yes, 100%, exactly. So they could probably say that it'll always be a percentage, but what the final amount would change depending on the reimbursement codes and value.
This is interesting. So thanks, April. This is all we see in this presentation, that machine learning, clinical praxis, and industry. It's all part of the same ecosystem, and especially in the imaging community. Correct me if I'm wrong.
Hmm.
And
Hmm.
I really appreciate this perspective. And for me, what is interesting is to speak about predictability of the biomarkers, which is something
Hmm.
that we can do also with imaging. And I was coming from a different world, right? So I'm looking at electrophysiology. So
Hmm.
now I understand a little bit better about, the contribution of imaging, and actually what is tied to biomarkers, which is not only, in a black box perspective, not only the results of a deep learning algorithm, but such as maybe algorithms that are part of your repertoire that have generative models, such as biophysics generative models. Do you know of some pathway, some research pathway that looks promising to you?
In terms of which, if you don't mind repeating that.
So it's more like a curiosity, an open question. I don't think there is yet an answer, but
Hmm.
maybe you're more familiar than me about biophysical generative models of disease. Exploiting
Hmm.
also only disease data sets that identify maybe ROIs, regions of interest,
Hmm.
specifically in the hippocampus, look at specific features of the feature set, like pre-selection of features. If you have the diagnosis chiming in first from the human clinical staff, and then having that input to pre-select the features, and then having a biophysical, spatial, physiologic, functional set of algorithms that identifies, I don't know, specific areas
Hmm.
or specific metabolic phenomena, like we were commenting before, like visual potentials in the brain, or areas of specific lamination in the cortex. So these biophysical models, if they
Yes.
could inform machine learning as
Mhm.
priors.
Yeah, so that's a great question. And um, I definitely think that having this prior information would is helpful, right? I mean, if you because creating a tool that's just going to work equally as well for everything that you give it, that's not possible, right? And so if you're able to narrow it down, you're kind of narrowing the scope of the tool, right? So if you're getting this external input, for example, like what you were saying about if the doctor says, hey, this is Alzheimer's disease, right? Like, then okay, I'm going to go look at the hippocampus, right? So you can kind of activate specific apps or tools based on, the direction of the physician. The biophysical models, I think, are, probably not best elucidated with structural imaging, but I'm sure that it's powerful, but I have no doubt that it's probably difficult to do that.
Mm-hmm.
So to develop a model that for such a non-linear kind of complex phenomena, I'm sure that it's not easy. And for that, I would feel like you would need more signaling data, right? Things that change with time,
Yeah.
are related to function, um, more than the
Metabolism.
structural. Exactly.
Because I was fascinated by your suite of algorithms, because I think I picked out of your one of the previous images, I picked Bayesian methods, and then I thought about having some priors there, and then since I was working with electrophysiology before and also with visiting labs, I made the connection there, and I appreciate the difficulty of applying it to structural imaging. And I'm fascinated by the topic.
No, and I think the interesting thing is that, like, we all work in disparate we work in silos, right? Like, but then there's great events and um, organizations such as this that kind of brings these disparate researchers together, and you can kind of see that there's a common theme. So, for example, like how you were talking to me about EEG and what you're doing with the EEGs, we're doing similar things in structural imaging, right? And so there's probably a lot of lessons that can be learned from, the similar but disparate areas.
Definitely, I
And there's
appreciate this
lots of
comment.
overlap.
I wish in in collaborative science, I wish we would be in a situation like astrophysics or theoretical physics, that there will be a CERN of neuroscience and Large Hadron Collider of neuroscientists that agree all together all over the world to point their radar into towards a certain, instead of galaxy, a certain disease, and try to solve that problem all together. That could be powerful, but we're far from that. But maybe a change in policy and a change on authorship, all these nice things will be
I think,
beneficial.
honestly, I think that research is getting more multidisciplinary, though. And I think the reason why it's getting like that is because in order to realize anything tangible and practical, you can't work in a silo anymore. You have to have multiple people as part of your team. Like, I work with, you know, radiologists, neurologists, pathologists, biostats, psychiatrists. And so, and each person kind of brings a unique point of view and aspect to the project that's definitely relevant because it touches on their work and their understanding in some way. And even in terms of, besides the clinical collaborators, like, to do this field well, you have to, or to be successful and to, you know, progress in this field is not just a ones and zeros game with the images. It's not just data that you're working with. You have to understand the how it's acquired. What is the acquisition technology, the pain point of the physicians. And so it's truly a multidisciplinary field, I believe, for, you know, some of these more domain specific image analysis, AI, machine learning. is more domain. You have to have domain expertise, which is not just how to develop a model.
It's
It's
a complex
yeah.
system, and it reminds me of I would make an analogy that is a little bit it's a little bit strange, but it's a little bit like in construction. Like a building has different parts of the building. It's almost like a human being, because it has, cables that are the nervous system. It has windows. It
Mhm.
has, concrete. It has, all sorts of. It has basement.
Structural.
Structural, construction. The field of construction has evolved as a field, trying to get rid of the bison and get more building, done in a amount of time per unit of time. And one of the biggest problems that has been solved in the book that was reading is that work has become multidisciplinary, almost like in a clinical practice where the different specialties are in place. But domain experts know about their specialty, but they will find a way to speak with each other, not only across centers, but also, and most importantly, to have this building built or to have this patient attended to. And in general, in surgery, for example, as in building a concrete apartment building, the specialization is important as much as communication, and that was a central point.
100%.
And then communication is, your presentation is a great example of communication and flows, collaborative flows, and then best
I
practices.
try to tell my students and my children that if you, I definitely tell my children who are just learning to write and read, and the older boy, he likes doing math, but he doesn't like writing. He says, "Oh, I'll do fine on science and math." And I said, "Yeah, he wants to be a scientist, an inventor." And I said, "Well, if you make a great idea, but you can't tell anybody about it, then that idea dies right there." And so, this is something also that engineers are unfortunately famous for a little bit, is that, we're real good at crunching the numbers and designing and optimizing, um, and but maybe the on the communication front is not as strong. So I definitely try to support my students and their communication, and I try to get them to explain to me what they're doing in a good way, and that can be tricky sometimes. But even at the undergrad level now, in you would have liked the project that I did a few years back. I taught biomedical signal processing, and I had a competition in the class, and it was for EEG seizure detection. And so they had to use like handcrafted feature extraction. They weren't allowed to use any deep learning. The data set wasn't big enough. And so they had to detect alpha waves, gamma waves, and do some stuff with them. And then in the class, I made them do something called a power pitch, which first of all, everybody had to present their accuracy. So that was kind of a competition, who gets the best result. The students loved that. But then second of all, they had to present what they did in 5 minutes. And it sounds easy, maybe, but when you've been working on a project on the ones and zeros for an entire semester, to come and take that step back and say, okay, why did I do this? But the students really got it, and they were great at it. And because they spent 1 slide on introduction, like 2 slides on the methods, 3 slides on the results, 1 slide on conclusion. And so the meat and potatoes had to be there, and there wasn't so that was one thing we did to focus on the communication of engineers.
Yeah, it's great.
But
It
you're
sounds
absolutely right. Communication is
spot on.
so important.
And then the other aspect, and I love your example, the domain experts within field communication, whereby technical personnel has to explain to colleagues what they did,
Exactly.
and that's beautiful example. And then the even more challenging example is when you have to explain it to anybody, right? Like what we're doing now today is for a bigger audience, but it's specific enough that can still understand what we're talking about, but even to push the envelope a little bit to take it out there to a different audience. That would be a nice exercise too, as we do have a comment from the audience from Alfredo. Hi, Alfredo. And he says that there is a big problem where the same thing gets called different names in different fields, and he points out how a shared lexicon is key and important in this communication.
Yes.
And I totally agree with that.
Yes. And hi, Alfredo. Thanks for that great question. And yeah, that's definitely something tricky, even for me now. One of the like in deep learning, a lot of the things that so I'm a signals and systems engineer. So we design filters, we do a lot of frequency analysis, and I was trained on how to design those handcrafted features, right? So I want to detect intensity, I want to detect localized texture. So the way we do that is usually through various types of different filters that we design for images, signals, all different types of things. So then when I started getting involved with deep learning a number of years back, and I had to figure out what an activation map was, it took a little bit of time, but it's literally the filter responses after filtering. So that was tricky for me for a little while because as an engineer, we're taught everything in terms of filtering and filter responses. So I definitely agree, and I wish that would happen because it would make my life and my research so much easier to understand different domains. Because that's really when you start to kind of get the interesting things happening.
Yes.
If you're in your own space and you do your own thing and you only look at what neighbor X and neighbor Y are doing, you did incremental. But if you can go to the mathematics field and say they came up with a new optimization method, I'm going to use that for medical imaging, for example. That's where the big kind of big moments happen in science and research.
I think what you're mentioning is, correct me if I'm wrong, is the, having to be exposed to mathematics in collaborative projects or grants or, applications where many people from different fields have to come necessarily together to solve different parts of the problem. And that's, for example, the exercise that was exposed to, that is a good example in my opinion, whereby you are forced to communicate in a clear way and get over your lingo of your field, because you do have people in the room that speak the different language, and such as the perfect example you are making with mathematicians. And then the best room is writing a grant together and having to see what you can learn from them, and vice versa.
I would also even extend that further to now that this technology is going to be touching the clinical side of things, right? The clinicians need to be made aware and to understand. And that was something that that takes a little bit of practice, because especially if you're a tool developer, you're used to going into the ones and zeros, the noise distribution, the this, the that, and none of that is relevant when you're talking to a clinician, right? You can describe the challenges that you're finding, what we have to overcome,
Yeah.
But what it is specifically and is too much.
Is the patient gonna be okay?
Yeah, there has to be some universal language almost. I gave a talk a few years back for this group called AI Med, and it's actually a clinician-led organization that is trying to actually make AI go into medicine, and it's a pretty big organization. And I gave a talk for clinicians, and it had the language that you use has to be in the middle, because I can't be telling them too much about the ones and zeros of things. It has to be a little bit more big picture. And similar when they actually talk to me, although I read medical papers and I'm not medically trained, so they have to have the universal language with me. And so there has to be some middle ground that allows us to communicate with one another in order to realize these tools, because an engineer cannot develop it by themselves. A doctor cannot develop it by themselves. It has to be a union. And without effective communication, really brings back to your point, Chris, is that doesn't happen.
Yeah. Or it takes
too long. Sometimes, or the engineer might make something that's really cool and but it's never used. It sits on the shelf. Mm-hmm.
I am on the same page.
Yeah.
And I wish, and then conversely, right? So the clinician has urgencies that we don't understand, and then we don't serve, and has prerogatives that have a different goal-oriented, approach and language. So yeah, the best way, like we were making an example of, is when you start working together, you will overcome if you have a common objective, I think.
Mm-hmm. Yeah,
and in this case,
sometimes when I even when we've developed a new biomarker, we've done the statistical analysis, we've done the whole pipeline, and talking to a radiologist, like one of my main collaborators for many years, he just brings the clinical lens, and he's just like, well, why does that matter, or how would this help somebody? And even though I've been designing these tools for a number of years, and I feel like I do have that clinical focus and that clinical view of things, he always brings another view that I didn't see, and it always makes the product, the research product, better every time.
Fascinating. It's spot on. It's a great contribution, actually, to underline the effectiveness of different domain expertise talking together towards a common goal, because it has value. It's more than the sum of the parts. And Epre, this presentation and these insights were terrific. I had a great time, jamming around these topics. It's also my interest, and I know you're doing great things and great projects also for the people that are involved in the studies. So thank you for that. I really appreciate that.
Thank you.
Yeah, so thank you for being a great guest today. And I would like to close with some final remarks. So, Epre, your contribution is the last podcast of the season. And then this year we had 6 episodes, so number 6, Dr. Epre Khademi. And we will have a pause until next year. And this season it was specifically, as you have seen, Epre, oriented towards applications, either hardware or software, like you presented. And the previous season was in retrospective about the synergy between market and academia, with a presentation from startups. The next season will be a different topic, which is mentioned en passant also in season 1 and season 2, and certainly in this podcast today, was about data, and then and will be about how we deal with data, especially clinical data, right? We spoke about the HL7 cloud, format or protocol, if you like, the DICOM PACS protocol. We spoke about these protocols that are clinical and demand high security of the data, anonymization. In the next season, we'll speak about these topics, not specifically to the clinical domain, but also about the clinical domain. But also we will introduce, broadcasting of data, the topic of broadcasting, ownership of data, the right to retrieve your data out of a data set that you are being informed to be, monetization of data.
Yes, that's a very, very interesting topic and loaded topic.
A loaded topic, and then that recently in Europe, the MDR protocol legislation has been introduced and makes life not easy for small startups that have to transition their data models to a new data model that is highly regulated. So there is an industrial commercial aspect and then consequence to that, and it's going to be, regulatory bodies have decreased their presence on the territory in Europe. I don't know about North America, but there's a big demand of that, and it's not a sustainable model. So there are some gaps to fill in, and neither for the companies involved in this data crunching business model, nor for the experts that have to certify the compliance of these solutions on the side of the regulatory bodies, and so it's a big problem.
Yeah, I was going to say that in Canada, there's some law that the doctor that basically, I guess the doctor of the institution that acquires your data, they're the owners.
Oh, you have to sign a waiver?
No, you do not. There's a law that many, many years ago, 1989, I think it's called the McDonald Law or something like this. And it basically was about that the patient has the rights to access their own data, but the doctor is the owner of it. And so this is what the governing law is now in Canada. And this is why some institutions are able to monetize the data. They're able to sell the data. So yeah, so all these issues that you were talking about, I can see how this can be many episodes, because you're right, the patient doesn't get any royalties, and they have, in most cases, they have no idea that their data is being used. So because it's all retrospective data, right? You don't need to get the patient approval for retrospective data.
And then it's almost it's really almost advisable to do like artists do to preserve their art, to come to the doctor with your non-fungible token and say, hey, this is my data. When it gets out of my body, it's associated with an NFT. I can trace it or something like that.
Yeah, exactly.
So there's more to say about that.
I think you wouldn't like to know where it goes, to be quite honest.
Oh yeah, but once information is power, and it's in the hands of the population, and then they can decide what to do with that, even get royalties. And it's transparent.
That all sounds like great.
Stay tuned. And I really love the conversation tonight, and I appreciate your time, April. And hopefully I'll see you again in the next episode, and then anytime. And if you like, you can leave your contact. I don't know if he was in the presentation for being reached out.
Yeah.
You can also do offline. So this Cloudcast text chat is going to be accessible to all subscribers also after the episode.
Okay.
Thanks everyone for this wonderful discussion, and thanks to the audience for the participation and the question. The audience showed a lot of interest, and thanks April again. And I wish
Thank you for
everybody.
Inviting me. It was interesting, very fun actually.
I had fun a lot, really. Yeah.
That was a great discussion.
I see you.
All the
I
best.
wish all the best for the
Yeah.
festivities
Happy
to
New Year.
everybody. Happy New
Exactly.
Year. And I'll see you in season 3.
Great. Thank you so much.